Hello everybody. Today we are going to be looking at more power. So I was trying to determine what I would call this lesson. I just wanted to call it more power because we are going to be analyzing power in a steady state configuration with our voltage source or source being a sinusoid. Okay, so first we're going to look at this picture and we are going to look at a network in a circuit, just like what we did with R equivalent and V Thevenin and I Norton. Except this time, like I said, the network is going to have capacitors and inductors in steady state, with the source being an alternating current. So the idea here is to find how much power is drawn by this network. And we are going to use our same idea, our same principle, P equals IV, except because it's a sinusoid, we have different powers. Like right here, we have like a high amplitude right here, and then low power right here, and then something in between. So what we're going to do is average it out, and we're going to look for P average or P bar. And I'm mostly going to use P bar for this. So refining our definition, we're going to have our P right here, our regular power, V of t times I of t, inside an integral to show averaging, and it's going to be the average 1 over t of the period, right? And the period, if you guys remember, is, well, actually, let's back up. Right here we have omega, right here, and omega is made up of 2 pi f, right? But f is also equal to 1 over t. And so we are going to put 1 over t into this. So it's omega equals 2 pi 1 over t. And so t is equal to 2 pi over omega. So that's what our t is going to be. But we've chosen to use the t period so that we don't have to write this all the time. Now, you probably don't want to be working with an integral every single time, like rederiving and rederiving, putting in your specialized, your specific V of t and your specific I of t into here. So we're going to go ahead and derive a general formula that you're just going to use for this lesson. So the first thing that we're going to do is just directly put in our voltage and our current. And our voltage consists of Vm, which is the amplitude of the voltage, our sinusoidal component, or omega. And then for current, it's our max current or amplitude current amplitude, the sinusoid, and then a phase shift, a phase difference between V of t. So what we're going to do is plug this directly into the formula, 1 over t, 0 to t. And V of t, I'm going to go ahead and just move the constants to the front and have cosine omega t times cosine omega t minus phi dt with respects to t dt. Now we're going to have to dig back into some archaic math back in high school, or if you're already in high school, then good job watching this. We are going to go ahead and combine these two guys, right? And we're going to use the infamous trig identity. And it's very good to know these identities. And I spelled identities wrong. Because they can help you simplify these kinds of equations, especially for proofs or derivations. So we're going to use this one. Now this is a popular one. It's used for various derivations, like in signals and systems, for things called beat notes and stuff like that, which hopefully I'll be able to make a video on one day, or a video series on one day. But basically, we're going to go ahead and call A omega t and B omega t minus phi. Okay. And so we're going to go ahead and apply that to our derivation right here. We're going to take Vm and Im out because they're just constants. And we're going to go ahead and simplify this. And I'm going to put cosine omega t plus omega t minus phi plus cosine omega t minus omega t minus phi dt. And because the 2 is a constant, I'm just going to put it outside as well. Now, the good thing about this is we can simplify this further. This is going to be 2 omega t. And these guys are just going to cancel. So we're going to go ahead and split up the integral. I'm going to call this k so I don't have to keep writing it every single time. This is going to be 0 to t. And bracket cosine 2 omega t minus phi dt plus the integral from 0 to t cosine negative phi. Now I'm going to ignore this negative because a cosine is well, regardless, it would have been canceled out anyway, but because of this negative right here. But it's an even function, so cosine's an even function, so all negatives would have died anyway. So we just have this. And if we solve this out, we're going to get k, and then cosine 2 omega t minus phi. So the integral of cosine is just a sine, right? And we're going to have sine 2 omega t minus phi from 0 to t plus, now this one is a constant. This guy's a constant, so we can technically take it out. And the integral of a constant is just that variable, so it's with respect to t, cosine phi from 0 to t. Oh, that was a bracket. And now we can go ahead and subtract. So we have sine 2 omega t minus phi minus sine 0, essentially, plus t cosine phi plus 0, because we have this t, and that's where the t, where the big T, the big period, goes, and we put our 0 right there. Now the cool thing about this is that we have 2 omega t right here, and remember what we called t? We called t this right here. So if we supplement this t in for 2 pi over omega, like so, we're going to get in this right here, this simplifies down to the omegas cancel, and this t is, that, so it's just going to be 4 pi. Now, what do we know about sine? Well, sine of 0 is 0, and so is sine of 2 pi is also 0. And any odd of sine, any odd multiple of pi, any even multiple of pi is just going to be 0. So this guy right here cancels out to 0. This guy cancels out to 0. So what are we left with? t cosine phi. And so we can go back to our k, which was just Vm Im over 2t times 2 cosine phi. And here we have officially derived a general form for the power average, which is 1/2 Vm Im cosine phi. Now this right here is very important. This is called the power factor. And we'll look a little more at that in this video. But remember that this power average has a sinusoid. So we're actually missing half the story here. Remember, our z is equal to r plus jx, right? Because z, the impedance, is a complex value. And this power only shows the real portion of the power. Because if we have an imaginary portion, if we have complex numbers, if we have capacitors, inductors, or some sinusoid, we also need to take into account something called reactance, okay? Yes, something called reactance. And that's going to be represented in Q. And I'm not going to go through the imaginary derivation. That's up to you guys. But it's essentially the same thing, except it's sine now, sine phi. Okay? And the units of power are watts, and the units of Q, reactance, is VARS, VARS, or correct me if wrong, I'm pretty sure it stands for voltage, it's I just had to look it up, unfortunately. It stands for volt, ampere, or amps, reactive. And this is just the reactive power. So basically the power switching between the capacitors and the inductors. Okay, so now that we've derived the main power function, let's go ahead and derive some other different forms of the power function. So we know that power itself can be expressed in two other different ways, v squared over r and I squared times r. But this time, because we have an imaginary portion and it's a complex number, we have to take into account the reactance, right? Which is denoted as x. So we have our total impedance equals r plus jx. And I have this little visual right here to help us out. And so basically what this is we have our impedance, right? And our impedance is split between the resistive part and the inductive part and the capacitive part, right? And yeah, the angle between these, the magnitude, the total magnitude, the complex magnitude of the z right here is going to be this vector right here, and the phi is the angle between the magnitude and the real portion. Okay, and so this ratio right here gives us cosine phi is equal to the adjacent, right? The adjacent over the hypotenuse. And knowing these relations, we can get all of these different formulas, okay? So here are all the formulas for the P average, and here are all the formulas for the reactive power, the power that's measured in VARs, okay? And so we'll take a specific look at the P average because, I mean, that's what we did last time, and it's pretty easy to derive the others. But basically, what you're going to do is you're going to start with your P average is equal to 1/2 Vm Im cosine phi. right? The magnitude of the voltage and the magnitude of the current times the power factor that we have right here. And using the fact that this is the real part, R, and this is the imaginary part, X, we can simply just write things in terms of each other, right? So our and then we actually need one more very important rule, which we can't forget. It's Ohm's law. And we have to generalize Ohm's law a little more, and it's going to be V is equal to, we'll call it big I this time, times Z, okay? Because it's no longer just R, it's also Z. And as such, we're going to basically turn them into these kinds of forms right here. So the first form that we're going to look at is the Vm squared one with this ratio right here. And so basically all we're going to do is we're going to eliminate the Im by taking Ohm's law and dividing like so, like this, Z. And we'll just say it's the absolute magnitude already because we don't really care about the negative sign in this case. And we have 1/2 Vm, and then this is actually Vm2, the Vm maximum, because that's not the average power that we're looking at. I mean, Ohm's law is showing these maximums right here. And we have our power factor right here. So actually, we've derived not just this one right here, but we've also derived this one right here, where it only has just the magnitude of the complex impedance. So we have Vm squared cosine phi over magnitude Z. And we actually get this one right here, the one with the Z squared and the real part, from this relationship right here. So the cosine, this power factor is related to the impedance, and it's related to the power, okay? So all we're really going to do, this is actually really not deriving, it's just plugging and chugging. So we know that cosine phi is equal to the real part, and if you're not comfortable with looking at it like this, the real part of Z, you can always just substitute this with R, okay, for resistance, the resistors, the ohms, right? Well, they're all measured in ohms, but like, you know what I'm saying, these, right? And then we have our Z squared, because this is the ratio, the cosine phi is just a ratio, the power factor is just a ratio. And likewise, we'll start with the same P average, Vm, Im, cosine, don't forget the 1/2, phi. And this time we're going to change the Vm. And we know that the Vm is just going to be Iz, right? I magnitude Z. And so it's going to look like this, 1/2. You plug in the In because it's replaced like that. And it's just going to be Im squared Z cosine phi right here. And I've put the absolute value bars right there. And once again, we can get our ratio right here. And so the ratio is just Re, the real part of Z, over the magnitude of Z. And once again, we plug it in, and we just get this. Okay? Simple. So that's the first four equations, and Q is exactly the same thing. But instead of looking at the real part, we're going to be looking at the reactive part, right? And I personally think it's kind of a misnomer to call it imaginary because it has real implications. It's just, I think that we do this because we need another place to store stuff. If we can put it in a two-dimensional graph, then we can store an extra idea, and that extra idea is called phase. And this phase, right, it's just super useful in anything EMAG. Sorry, my Outlook calendar keeps going off. Okay, let's go ahead and do some practice problems. So this is the first problem, and it's pretty specific. It says find average power and power factor of the circuit. So basically, we're asking how much power does our network draw out? And right now, it doesn't really look like a network that, like, it doesn't look like this right here, but we can make it like that. So the idea first is to turn everything, it's going to be somewhat similar to the algorithm that we used for steady state analysis with, nodal analysis and loop analysis in a steady state configuration. And so what we're going to do is, instead of actually turning the V into the frequency domain, we're just going to turn all of these guys into frequency domain because we want to find the impedance. That's very important. In these power problems, you want to find the impedance first. So I guess I would say it would be step one is find impedance. And we already know the impedance of our resistor, which I'm just going to call R. R or ZR to be consistent, and that's just 10 ohms. And we also know the impedance of our inductor. It's just ZL is equal to J omega, and our omega right in this case is omega equals 20 from our cosine function right here. So it's just 20 times the henries, which is 1/4, and so that's J5. And then finally we have the capacitor, the impedance of the capacitor. And that's going to be 1 over J times 20 times 1 over 50. Okay. And that's going to be, we'll go ahead and move the J up, negative J, 5 over 2. Right? And then to find the total impedance, right, it's going to be Z is equal, and all of these guys are in series, so we simply add them up like regular resistors. And so we have the real part right here, and we have those imaginary portions, J5 and negative J5 halves. That's going to equal Z is equal to 10 plus J5 halves. Now, the next idea is to find the magnitude of this, which is very simply just 10 squared plus 5 halves squared rooted, and that is going to equal approximately 10.3077. And so we have one of the components already. We have the Z right here, right? And for the sake of completeness, we can go ahead and draw a graph already, and this will be imaginary, this will be real. Won't populate it yet, but the next thing that we need to do, we actually need to find the average power. And so the average power, we can actually use one of our formulas already. Just kidding, we can't use our formula yet. We need to find the power factor first. So the power factor, if you remember, is just the ratio between the real part of the circuit, of the impedance, over the total magnitude of the impedance. And we know what the real part of the impedance is. It's just 10. So we have 10 over 10.3077. And that is going to equal to 0.970. And this is what this number is saying, it's the power factor. So 97% of this power is being extracted, right? And the idea here is that this guy right here is always going to be larger than this guy right here. It's going to converge to 1, okay? Because this is the total amount of I don't want to say the word resistive. Impedance. There you go. It's the total amount of impedance, because we have to consider the tango, the dance between the inductor and the capacitor, and we have something that's actually dissipating stuff. These are just transferring power, transferring energy between one another, albeit not perfectly, and so we need to take that into account. And so it's going to be a factor of, that's why it's called the power factor. And we can actually take this ratio right here and find the phi, and this is where I was going at with the graph. So 0.97, and I believe that's going to be, I'm going to have to calculate that. That's going to be about 14 degrees. And as it goes lower and lower and lower, right, so like this. So currently this circuit is more inductive, and it's at 14 degrees, about 14 degrees. And so that means that the inductor is the one that's really, you know, producing this impedance, right? And that kind of makes sense, right? Because we have an impedance of 5 right here, and then 5 halves down here. The capacitor is contributing to negative 5 halves. And so it's less, right? It's half of that. So it's going to be a little more inductive. But the idea is you want to try to get it down to just the resistor removing power. You ideally don't want these guys to be fighting each other, okay? And so that's what this graph looks like. And so we found the power factor, so that's actually the second part of this problem done, which I should have probably wrote it in an order that you're going to need them. But now that we have the power factor, we can use one of our equations, so step 2, to find the P average. And we know from our voltage right here that this is the maximum amplitude, and then it's going to be oscillating around that. And so Vm is going to equal 8 volts. And so at this point forward, we just have a simple plug and chug. 1/2, and we know it's 8. It's going to be 8 squared. We're going to use the P is equal to 1/2 Vm squared, and then because we already have the power factor, we can just do this. And either way, it's going to work. You can use also 1/2 Vm squared over the real part of the impedance divided by the square of the impedance magnitude. And you can try it out. It's going to equal the same thing. So that's 8 squared, and the power factor is just 0.970 divided by the magnitude, which is 10.3077. And that's going to be approximately 3.0117 watts. And that's the answer. So these problems are quite simple. They're just preliminary problems, and we're going to go ahead and do one last one, and then we'll call it a day. Okay, so now we have another kind of system, network. And so the idea stays the same. All we're going to do is step 1, and I'm going to go through this a little more quickly, but we're going to find the impedance. So we're going to say, we already have the real part. I'm just going to write it like this. Actually, no, I'm not going to write it like that. First of all, we're going to have to get these guys together. And so the Z capacitor is going to be 1 over J times 2, because the angular frequency is 2, times 1/2, and so we just get negative J. And those guys are in series with each other, so ZCR2 is equal to 1 minus J. And we have our Z inductor like that. J. 2 times 4 is just J8. These guys are in parallel with each other, so it's going to be ZL or LCR2, and that's going to be 1 minus J, J8 over 1 minus J plus J8. And we're going to get 8J, or let's just say 8 first, because negative J times J is is positive 1. And so we got 8 plus J8 over, and this is simple, 1 plus J7. We're going to get rid of the conjugate on the bottom. We're going to get rid of the complex number on the bottom by using the conjugate. And we're going to get 64 minus J48. Pretty sure you can do the math. It's just foiling. And then down here, we're going to get 1 plus 49, which is just 50. And simplifying that down, we get 1.28 minus J 0.96. And so this configuration right here, that configuration is 1.28 minus 0.96, J 0.96, and we're going to add 2. So we're going to get our Z total, this time we can call it Z total, is equal to 3.28 minus J 0.96. And then what we've got to do now is find the magnitude, which is just going to be 3.28 squared plus negative 0.96 squared rooted. That's 3.4176 ohms. And to find the phi, all we're going to do is tangent negative 0.96. So that means that we are in the fourth quadrant, and this is more capacitive. Okay, so think of capacitive as being a subtraction. Okay, in this case, 3.28, and that's going to be approximately negative 16.31 degrees. And so on our graph, it's going to be more capacitive. It's going to look like this. 16 degrees, like so. And so the we can say step 2, the power factor. So the power factor is just going to equal to cosine negative 16.31 degrees, and that's about 0.9597. Okay, 95%. Finally, we are going to find the average, and we can knock out the reactance as well. So using one of our formulas, we'll just use the same formula because it's all the same thing. Just remember all of them. So 6.5, right? And the 6.5, I got that from here because that's the maximum amplitude. And we're going to multiply that by cosine, the power factor, sorry. We'll just go ahead and multiply with the power factor. And we're going to divide that by the total impedance, which is 3.41. And we're going to get 5.93 watts. For the reactance, the exact same method. We're just going to have 1/2 times 6.5 squared times this times sine of phi, and we actually don't know what sine of phi is, so we're going to have to directly plug in 16 degrees, negative 16.31 degrees. So our reactance is actually going to be negative divided by 3.41, and that's going to equal approximately negative 1.74 vars. And that's basically it. We found our reactance, we found our power, we found our power factor, and we even added a bonus of graphing out our impedance and seeing whether or not it's more capacitive or more inductive. Okay. Now, in the next video, we are going to be actually taking this and solving for trying to get a specific power factor. Okay, maybe the city grid, you're an electrical engineer. My professor used this analogy. Or allegory, really. It's more of a story. It probably happened to him. But maybe the city of someplace asked you as the engineer that you have this network and it's full of inductors and capacitors and you only care about the steady state, which is pretty ideal. And you have a very, very sucky power grid. It's like your power factor currently is only like 0.8 percent, or so 80%. Basically, can we find a component right here, that can make the power factor bigger, right? And so we're going to use geometry in next lesson, and hopefully you find that intuitive. And then after that, we are going to actually learn how to maximize power in this steady state with the reactance, and that's it. So hopefully this video was useful. Please, once again, point out any mistakes that I make, and if you have any questions or you would like to see any more problems like these, please, comment it down below. And yeah.